Let's learn about fundamentals of deep learning. First of all, what is deep learning? So earlier, compared to artificial neural networks or compared to machine learning, in which there is a handcrafted feature extraction and that feature being fed to network, thus we can say not deep learning. If the feature is extracted by the model, and that happens by stacking this layer upon layer, which acts as like extracting this information and then information out of the previous layers output information and like that, and finally boiling down it into crisp information. Like example, if you're doing a car car versus bus classification, but information which will point whether the image belongs to a car or a bus, that information extraction using this multiple convolution, or now we have transformers. So whichever method, if we stack them together for feature extraction as well as and learning what the contents are, and then finally a classification or detection or regression into age, class, or things like that, whatever output we need. So if that happens with the stack of layers, then we will say it is deep learning. If it is happening with the just one or two hidden layer and output, then we can say it's not deep learning. It's like basically, if the feature extraction is not there, then we can say it is machine learning alone. And feature extraction is there based on layers, then we can say it is deep learning. Okay, this the grayscale actually, but yeah, this is one line we can draw. Yeah, so recently more deep, like much deeper networks are there, and if it is convolutional, then we say convolutional neural network, and if it is transformer, then we can say transformer, and based like recent GPT and all are based on transformers only. Again, the concept remains same. You stack together like whatever this feature extraction or layer, stack them again, keep on attaching, and we can get more and more abstract information from the input. And then finally, we can use that abstract information to do like to generate suitable outputs. Now, this in this weights and all these layers basically is what we call the model. Model is what learns all these layers connected together, which acts as feature extractor and this final classification or other thing, detection or regression. So this is what is a model, and our whole need for training is to calculate the weights such that we get the desired output from this input. And if it's a very simple problem, like let's say classification between plus symbol and minus symbol, then we don't need all these deep layers and everything. We just need maybe one convolution layer and one dense layer. That should be sufficient. But if the problem is more complex, we need to differentiate between the car images. In that case, it is more complex. So based on the complexity, we will need more depth. So if we are putting a big model for a small problem, then we say it will overfit. Basically, let's say we want to connect, we want to fit a line for a set of points. If you're fitting a line, then instead of fitting a line, if you want to fit a curve, so you can draw a curve, a smooth curve, or you can draw a complex curve which connects all the dots. but if a new input comes, but that's not what we need. We don't want, there is noise always, like in all these things, there will be noise. So it should not go and fit on that data, on the noise of data. Instead, it should learn to generalize and create smooth curves. So that is applicable in even in car or whatever images or whatever data. This overfitting versus generalization is there. So main trend of a generalized or overfitted model is it will give good result on training set and poor result on validation or test set. Then we can say it's an overfit model. So actually overfitting is a good practice in the beginning, in the very beginning of developing a model. It's a good practice to just overfit and see whether at least the model is able to overfit. If a model can't even overfit, that's a bad sign. Better to go away from that model. So in training, we need to familiarize few times. One is this batch size. So earlier in the convolution, like when we discussed about back propagation, we were talking about one input and one output. And the output, if it is wrong, we will propagate the error back using back propagation. Now, there is this concept of giving, instead of one image, give n number of, a batch of image as input. In that batch, one image might be car, another image might be bus. Let's say we have a classification of bike, car, truck, van, etc. So randomly, we will pick from our data set n number of images. Maybe there can be 2 cars, 1 truck, 1 bicycle, or maybe there will be all cars only randomly, can happen as well. So randomly taking n images or a batch of image as input, and the output of that batch is already known again. So we will predict for this batch of image. So what we can do is this convolutional operation, for example, we can simply calculate this. We have this GPUs, and this convolution operation can be done on this entire batch of image. So instead of one output, we will have that batch output, and this way in the GPU we just have to keep, let's say we have 3 convolution layers, and in each convolution layer, let's say we have only one kernel. In that case, these 3 kernels we can reuse for n number of images. Just that we need to store all this image input in the memory, and the intermediate result, whichever is required, we should be able to handle. So this way we can calculate we can predict in GPUs in a batch fashion. So one image at a time, we can give a batch of image at a time, and all these operations will be done on this batch of images, and we will get a batch of output. And then we can compare with the expected batch output and calculate loss. So advantage of this loss is it is more since there are, instead of one, since there are multiple outputs, the loss will be more stable. And there is also another advantage of, even if dataset is having little bit of noise, like some images are not labeled properly, still this loss will average out, not average out, that small mistakes will not be causing much of a trouble in the, at least for in order to get really good accuracy, you need to label all the dataset properly. But in the beginning, it might be okay. Like even if some samples are wrongly labeled, still network will be able to learn when we have enough batch size. So good idea to increase batch size as much as possible, given your GPU can handle it. And if it is CPU, better to the batching is again a computationally heavy process. So for training, it is always best to use a GPU and use the batch size which that GPU can handle. More the batch size, less there is chance for any erroneous image causing trouble in this weight updation. Because if you're giving one image and batch size is 1 and that output is not correct, maybe network predicted it properly, but still we will tell that okay, that is not the correct output because we have labeled it wrongly, and then we will make the weights, we will change the weight such that it matches with our erroneous output or basically erroneous label, and that way we are troubling the weight. Like there is good chance that this weights will not learn as we expect. All right. Then another concept is normalization of input image. So for these networks to be more stable, it's better we reduce the range of input, and instead of like let's say 0 to 256, 255 for images, we will compress it into -1 to 1 or 0 to 1 range. By dividing by 255, we can reduce the normalize this image into 0 to 1 range. So by giving such normalized input, this networks can be more stable. So it's not hardcore rule or anything. You can give raw image as well and train. Yeah, but it is always better to reduce the value input range to 0 to 1 in any problem statement. Then we have this learning rate. So we have seen that in the training, learning rate is an important factor in determining how much the weight should be changed. If it is too high, it will cause instability. If it is too less, it will take a lot of efforts to learn and become good model. Then this optimizer is what determines how this entire training like weight adjustments to be done, and there are different optimizers. Okay, we can read about that or we can come to that later. And then loss function we have already seen. The output, whatever is the predicted value and expected value. Between that, we need to write a function which will return the cost of this prediction. So basically, that's what loss is. If the predictions and expected outputs are same or close to each other, then loss will be less. They are different, loss will be more. We have regularizers. So this is for controlling the range of weights. So earlier we have seen this weights can have any value. So it's a good idea to limit that value range again, so that it might add to some stability. More stable network can be created by regularizing. So, but these days you can hardly see any regularizations because all this convolution and deep networks, they are able to learn and get good weights, stable weights even without regularization. But yeah, when need comes, go for regularization as well. Good practice. Now, what is TensorFlow and PyTorch? TensorFlow and PyTorch are frameworks that allows us to create this kind of networks and functions for inbuilt function for this loss and commonly used features, as well as this implementation of optimizers, regularizers, whatever we want. So these frameworks provide all the features required for creating and training, as well as finally inference of these deep learning models. We'll see more about them in the coming sessions.